Alright guys, so we're going to finish up section 5.3 today. Also, tonight for homework, you'll see on the calendar that I've posted a quiz review here at the end of section 5.3 in my OneNote. This has an example of all the different types of questions that could be on the quiz tomorrow. So there's 7 questions there, you try them out, and then the answer key is listed after that, so you can go back and check your answers. You want to make sure that you're able to do all of these problems. You will be able to use your calculator on the quiz tomorrow, but you do need to also show all of your work, showing how you set up each Riemann sum or estimate of the integrals. Alright, so today we're going to do explorations 1 and 2, and then we'll finish with example 4. So exploration 1 says, suppose we have a circle of radius r centered at the origin. We want to know the average length of the chords perpendicular to the diameter, and this is walking us through it. So this is a good example of the way a free response question might be set up for this type of a problem. Let's start by drawing a diagram of what they're asking about. So we've got a circle, and let's say that's our diameter, so it runs through the center of the circle, and a chord would be a line segment that intersects the circle in 2 places. So let's say this is our vertical axis, and we've got a chord a distance x away from that. So one thing that we know about this is that the line segment is going to be evenly distributed above and below the diameter. Another thing that we know about this figure is that a line going from the center of the circle to the end of that line segment is going to be equivalent to the length of the radius. So this is r, and we said this is a distance x, and that means that the length, by Pythagorean's theorem, of that line segment, just the top piece, is going to be the square root of r squared minus x squared. So then the entire length is 2 times that. Okay. So that's question 1. Show that the length of the chord at a position x is given by that expression. So we found that out geometrically. 2, it says set up an integral expression for the average value of the length of the chord over the interval negative r to r. So over here would be negative r, over here would be r. We just found our expression for the length of the chord. Let's call this L. So we want to find the average length of the chord. Now we found out the other day that the average value of a function is given by 1 over the interval length. So this is going to be r minus negative r times the integral from negative r to r of our function L. So that's going to be 2 times r squared minus x squared with respect to x. Now, again, this isn't an integral that we know how to integrate directly, but we can manipulate it slightly and figure it out geometrically. So let's simplify this a little bit. So this is going to be 2 over 2r, the integral from negative r to r. Now, this integral represents an area from r to negative r, and the function that we're looking at is the top half of a circle. So this represents the area of a semicircle. So the value there, if the whole circle is pi r squared, then the value there is going to be pi r squared over 2. So we're going to get 1 over r. And then this is the area of a semicircle, so we're going to have pi r squared over 2. And then simplifying that, we're going to get pi r over 2. So we've answered 3 now. We evaluated the integral by identifying it as an area. 4 says, what is the average length of the chord of a circle of radius r? So in the first part, it was very particular. We were looking for the average length of chords perpendicular to the diameter, and now they're asking us a different question, a more general question. Just what is the average length of a chord in a circle? Now, because the circle is completely symmetric about any axis and the diameter could run in any direction, we can extend the proof we did already to be any chord. So the answer to 4 is no different. And then 5, explain how we can use the mean value theorem for definite integrals to show that the function assumes the value that we found. So there must be some place in this circle that has a chord of length pi r over 2. And the mean value theorem said that if we have a function that's continuous on the region that we're integrating, that would be the case. And yes, this function is continuous from negative r to r, so it does in fact assume that value at some point. Alright, so let's move on to exploration 2. Instead of doing this as group work, I'm going to kind of walk you guys through it since we're not in class together today. So it says to copy the graph onto a sheet of paper. So here's just a rough sketch of that graph. And it says to choose an x value greater than a that's in the interval a to b and mark it on the x-axis. So here I've got the interval a to b, and I'm just going to pick a value for x. I'll put it here. Use a different color. We'll put it there. Alright, now it says using only vertical line segments, shade in the region between the graph of f and the x-axis from a to x. So we'll start here. There we go. So 3 says, your shaded region represents a definite integral. Explain why this integral can be written as the integral from a to x of f of t dt, and why don't we write it in terms of x? Okay, so remember that the definite integrals represent a area between the curve and the x-axis, and in this case we're going from a to x of some function. Now t is used as a dummy variable, and the reason we're using t is because it wouldn't make a whole lot of sense for us to say that the variable x is varying from a to itself. So t is used as a dummy variable since we're already using x to signify an arbitrary place on the interval a to b. Alright, so let's keep going. So it says, compare your picture with others. We can't really do that, can we? Notice how your integral depends on which x you chose. The integral is therefore a function of x. So if we had all done this together in class, it's likely that we wouldn't have all placed x in the exact same spot. And the point they're trying to make is that in turn turns this expression into a function that depends on x, or a function that gives us different values for area depending on how far over we let x be. So the integral that we've written down here is still a function in terms of x, because the area that it represents depends on how far x is away from a. And we're going to call that f. So we'll call this f. Or another way to say it is that the derivative of f is going to be equal to lowercase f, and the opposite way around, capital F is the antiderivative of lowercase f. Okay, so 5 says, recall that f prime is the limit as the change in f over the change in x as x gets smaller and smaller. Represent delta f in your picture by drawing one more vertical shading segment to the right of the last one you drew, and it's a signed area. So we'll go ahead and do that. So we're going to add one more rectangle. It's going to be here. We'll shade that in for clarity, and we're going to label that as delta f. Okay, and that's the signed area of that vertical segment that we've got. So it's going to be this negative area. We want to represent, for 6, we're going to represent delta x in our picture by moving x. We've got that on the number line here. So this is our delta x. And the last statement says, that small change in delta x is the thickness of your vertical segment. So 7 says, what is now the height of your vertical segment? So that height is our lowercase f. So if we look at it, think about what we've got here. F prime is equal to delta f over delta x. Now delta f was our, remember capital F is our area here. So delta f, represented in the shaded region in green here, is our small change in area, and delta x is our small change in x. So if we let delta x become very small, as these push together, if that rectangle becomes infinitesimally skinny, then the height is just f, or the same thing we saw here. If capital F is the antiderivative of lowercase f, then when we take the derivative of the antiderivative, like we're doing here, if we let delta x approach 0, then this ends up being just f of x. So this is the relationship they're trying to show you graphically. Okay, so using the result from exploration 2, let's answer example 4. It says find the integral from 0 to pi of sine of x dx using the formula that we derived in exploration 2. So the first thing we need to do is we need to figure out what the antiderivative is. So in this case, this is our function f. We need to know the antiderivative. So the antiderivative, in this case, capital F, is going to be equal to negative cosine x. Because if we were to take the derivative of that, we would get back sine x. So then, plugging that in, we're going to get the integral from a to x of f of t dt